Welcome everyone. My name is Orsolya Gáspár. I am an assistant professor at the Department of Mechanics, Materials and Structures at BME Budapest. The study I am presenting today on behalf of my co-authors István Sajtos and András Sípos as well is titled Safe Estimation of Minimum Thickness of Circular Masonry Arches Considering Stereotomy and Different Rotational Failure Modes. The structure of this presentation is as follows. I will briefly introduce the background and the motivation for this work. Then I describe the applied methodology which is based on our previous results. The third section is dedicated to the results, and finally I will summarize the conclusions. The slides are color-coded for ease of navigation. The colors labeling each section are shown on the left here. Minimum thickness analysis serves as the theoretical background to our investigations. The arc is declared safe if the thrust line, the line compressive forces follow through the structure, is kept everywhere within the boundaries of the arc. A minimum thickness arc is just thick enough to contain a thrust line. It touches the arc's boundaries at certain locations, at the locations of plastic hinges. It is known that the overall geometry of an arc influences its failure mode, number and location of plastic hinges. It has also been shown for the specific class of elliptical arches, which all correspond to the same type of failure mode and same number of hinges, 5, that the minimum thickness value does not only depend on the overall geometry of the structure, but also on its stereotomy. Hence, for a given overall geometry and loading, a range of minimum thicknesses can be defined. Furthermore, for elliptical arches, it has been proven that the catenary type thrust line resulting from vertical stereotomy leads to the highest minimum thickness value and upper bound to the above described range of minimum thicknesses. In the present study, we consider circular arches. These can be smooth, as the semicircular, which corresponds to a 5-hinge failure mechanism denoted here 5-hinge type 1, or pointed. Depending on its pointiness, pointed arches can correspond to various types of 5-hinge mechanism, the arrangement of hinges differing from the 5-hinge type 1, a 6-hinge mechanism, or even a 7-hinge mechanism. See the figure at the bottom here. An analytical proof that the list below is complete was provided by us earlier. Our investigation is focused on the 6-hinge and the 5-hinge type 2A, as they possess a certain geometric indeterminacy which will be more extensively discussed in the following. It is not straightforward that the dependence of minimum thickness on stereotomy holds for these failure mode types. This leads to the first question we investigated. Does stereotomy influence minimum thickness value for any pointed arc? Moreover, can stereotomy influence the failure mode itself, either the number or the arrangement of hinges? This is relevant as former studies derived the list below by assuming 1 fixed stereotomy radial. It is no secret that the answer to our first and second questions was found to be yes. It means we have a range of stereotomy-dependent minimum thickness values for a given geometry. Hence our final question reads, is there a specific stereotomy resulting bounding value minimum thickness to this range? Before we proceed, clarification of the key terminology is necessary. Stereotomy refers to the brick or stone laying pattern, but within this research, stereotomy is treated as a continuous function ordering the direction of the section to each point along the reference line of the arc. Catenary type thrust line results from vertical stereotomy. It is called catenary type as the resultant is tangent to this and only this thrust line at its every point. An important property of this specific thrust line is that it bounds the family of thrust line, stereotomy-dependent thrust lines generated for a given geometry and loading, assuming a statically determinate problem. We have repeatedly talked about a bounding value of minimum thickness, which might sound unusual, but as we have discussed above, depending on stereotomy, a range of minimum thicknesses can be generated for a given geometry and loading. The bounding values are the minimum and maximum of this range if they exist. The thickness is scaled by the radius of the arc, hence we use the notation T over R. In terms of modeling, we rely on the Hymanian assumptions regarding material quality, hence we assume infinite compressive but zero tensile strengths and no sliding along the sections. Consequentially, we only consider rotational failure. The arc is subjected to its self-weight only. The structural model is simplified. The self-weight is distributed evenly along the reference line of the arc regardless of stereotomy. This allows an analytical formulation of the problem. We use the geometric formulation of the minimum thickness analysis. The condition of equilibrium is that the truss line does not exceed the arc's boundaries, whereas yield occurs when it touches either extrudos or intrudus. For the problem is symmetric, only half of the arc is considered. The geometry of the pointed arc is described by eccentricity parameters xe and ye, describing the eccentricity of the symmetry axis and the shoulder line from the center of the circle respectively. The reference line is chosen to be the center line of the arc. The eccentricity of the truss line at the top and the bottom from the reference line are denoted ET and ES. They are unitless quantities scaled by the projection of the arc's thickness on the respective section. Please note that the topmost section is chosen to be vertical, whereas the bottom one is horizontal. We use both polar and Descartes coordinates. Their transformation is straightforward based on trigonometry. In case of polar coordinates, alpha denotes the internal angle to any point along the reference line and phi to any point along the intrudus or extrudus. The relation between the two is established by stereotomy. We apply the so-called plastic design methodology and assume a certain kinematically admissible arrangement of the plastic hinges. It is important to emphasize that within this framework, the relation of truss line and thickness is fixed. The arc is assumed to be at its limit state. Hence, instead of searching for thickness values, we search for admissible stereotomies for a given thickness value that renders it minimum thickness. The range of admissible stereotomies is defined based on equilibrium constraints, as briefly demonstrated on the next slide. Let us consider the semicircular arc with a suitably small thickness. Assuming that it is at its limit state, its array of resultants is uniquely defined based on the arrangement of hinges, 5-hinge type 1, internal hinge towards the intrudus. Now, we choose an arbitrary resultant vector E and check which parts of it are within the cross-section of the arc and which are not. The former are admissible, the latter is non-admissible. Equilibrium would be violated. This region is shown in orange. This means that for the respective point at the reference line, measured by alpha, I can define an admissible and a non-admissible range of points along its intrudus, measured by phi. Recall that the stereotomy function orders alpha and phi together. Hence, if I map this relation on the alpha-phi plane for a given thickness, I can construct the admissible and non-admissible ranges of stereotomies. The internal closed non-admissible range is marked light gray. Any stereotomy function touching it will render our given thickness minimum thickness. By varying the thickness, the size of the inadmissible range changes. It gets smaller if the thickness is increased and bigger if decreased. Limit is reached. If stereotomy is vertical, the internal range then disappears. It results an upper bound to the minimum thickness values. For a very pointed arc, which also corresponds to a 5-hinge mechanism, only a different arrangement, type 2b, internal hinge towards extrudus, but still only one internal hinge, a similar argument and a similar diagram can be formulated. Observe that now the inadmissible range is the outer one. Limit is reached again if the stereotomy is vertical. The two outer range then collides, but this results in now a lower bound to the minimum thickness range. Since in both cases the catenary type truss line provided a bound, below we use it as a reference as a likely candidate to result in bounding value minimum thicknesses for the rest of the failure modes as well. For any other type of failure that can occur to pointed arches, not one but two internal hinges are formulated simultaneously, one at the intrudus and one at the extrudus per half arc. This results a more complex diagram. The example in the figure shows a 6-hinge mechanism, with both an inner and an outer range of inadmissible points. It is easy to demonstrate that if we assume the location of truss line fixed at the arc's top and bottom as before, no admissible stereotomy can be constructed either if we increase or decrease thickness. This would suggest that no stereotomy-related variation of minimum thickness exists. However, it is not necessary to treat the location of the truss line point as fixed at the top. By decreasing ET, the eccentricity of the truss line at the top, admissible ranges open up either if the thickness is increased or decreased. Recall that the reference diagram is based on the minimum thickness derived assuming vertical stereotomy. This means that the catenary type truss line does not provide any bound to the range for these type of failure modes. The natural question arises, what is the admissible range of ET then? it is found that it can be decreased as far as -1. This turns the originally 6-hinge mechanism eventually to a 7-hinge mechanism, albeit this requires extreme stereotomies. Depending on stereotomy, the corresponding minimum thickness can be either higher or lower than predicted by the catenary type truss line. Moreover, if ET is set to -1, we can still modify ES, eccentricity at the springing. Limit is reached if it is also set to -1, turning the originally 6-hinge mechanism into a 5-hinge type 2B mechanism. Again, the resulting stereotomy would be rather unrealistic. Subject to stereotomy, the corresponding thickness can be higher and lower as well. ET and ES parameters represent the geometric indeterminacy of the problem. The admissible ranges of minimum thicknesses can now be determined. The diagram shown in this slide shows XE on the x-axis ranging from 0 smooth arc to 1 highly pointed arc. The minimum thickness values are measured along the y-axis. The ranges of various failure modes are marked with different fields and colors. The red curve running in the middle denotes minimum thickness values derived assuming vertical stereotomy catenary type truss line, while the black one represents radial stereotomy. The latter is in very good agreement with previous results of the literature. The very tiny range within them is the range of realistic stereotomies. We have emphasized previously that the catenary type truss line does not provide any bound for failure modes with geometric indeterminacy, and that is illustrated well here. Yet, within the realistic, from a practical point of view, range of stereotomies, the relation of the red and black curve is relevant. The catenary type truss line hence provides a practical upper bound for 6-hinge and lower bound for 5-hinge type 2A failure modes. So to conclude, we were able to prove that while failure mode is eminently determined by geometry, stereotomy can modify it. Generally, catenary type truss line does not provide any bounding value minimum thickness for failure modes with geometric indeterminacy. However, for realistic stereotomies, the catenary type truss line provides a practical upper bound for 6-hinge and a lower bound for 5-hinge type 2A failure modes. Thank you for your attention. Should you have any questions, please do not hesitate to contact me.